Hi guys, and welcome back for the next installation of Module 5, Equilibrium and Acid Reactions. Today we're looking at 5.1.D, which is our learning intention there is to investigate the relationship between our collision theory and our reaction rate to analyse our equilibrium reactions. So let's go. So just recapping of what we've done in Year 11 in Module 4, looking at collision theory. So our collision theory is that basically all our particles are moving, but they need to move with an energy and the right orientation for those bonds to break and then reform to form new products. So to reach this energy required is our activation energy. So if we're looking here, you can see here we have our reactants with a certain amount of energy, and this is the energy here required for the reaction to start. This transition state is just that period between the reactants gaining enough energy and forming the products. So this amount here from this point to this point is the activation energy required. Once they have that energy, they can go through to form the products, and here we have the products down here with a lower amount of energy, and in this case it's an exothermic reaction. So if we have activation energies that are low, then in both directions, then both directions of the reaction will happen, so the reaction will be reversible. But if the activation energy in either the forward or the reverse direction is too high, then that part of the reaction will not be able to happen. It's unlikely to happen. So if we have a low activation energy happening in the forward direction, but high activation energy in the reverse direction, then the reverse reaction won't take place. So you can see this here in our graph. We have our reactants that are just here. They require this amount of energy to get over that hump, enough energy for the reaction to happen, and then the reaction will proceed. But if we were to do that in reverse, we have here the products with a certain amount of energy. They've got to acquire this amount of energy to be able to break those bonds and go in that reverse direction. And if that's too high, it just won't occur. Here again, we have an endothermic reaction where the activation energy here is quite high, but once it gets up over there and it forms the products, then it only has a little small amount of energy to gain to go back in that reverse direction. So again, here, if it's a low activation energy, it's more likely that it'll be reversible than if it is high. Now let's have a look at this example. Here we have the diagrams here with our concentration of an ammonia reaction. You can see over here on our equation, 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Now if we have a look over here on the graph, at the beginning of the reaction I have 3 moles of hydrogen and I have 1 mole of nitrogen. So according to the mole ratios in the reaction and in the equation that I have on the right hand side there, you would expect that 2 moles of ammonia will be produced. So as the reaction is continuing, you can see that there is a drop off in the concentration of the hydrogen, also that of the nitrogen. But if you look at our concentration here of our ammonia, you can see that we start with 0 moles, as you would expect, because no products have been produced at the beginning, and it increases. But here we find that it flattens out, and it's not at 2 moles. So we can see that this reaction is not going to completion and forming those 2 moles of ammonia, but instead those 2 moles of ammonia with the right amount of energy and orientation are going and colliding and forming our hydrogen and nitrogen in the reverse reaction. And that's indicated here by this reversible reaction sign. So you can see here our graph tells us quite a bit about the reaction. So if we're looking at these reactions, we can actually see from these graphs whether the reactions do go to completion or whether in fact they are reversible there. And at this point here, you can see this is the point where our graph starts to level off. So you know that we are reaching equilibrium at this point. So you can see that this is time. So as time progresses, it is decreasing, but it eventually will level out, and the same for the nitrogen, and the ammonia will increase in the concentration and again level out there. So what's happening here in terms of collision theory? At the beginning of the reaction, we have 3 moles of hydrogen and 1 mole of nitrogen. There is a higher concentration of the particles there, therefore they're colliding more frequently and driving that forward reaction. As the reaction progresses, the concentration, therefore the number of particles, of the hydrogen is decreasing, and so there are fewer particles there that are colliding and producing those reactants. But what's happening on the reverse is, as the reaction is proceeding, we are actually getting an increased number of particles in the products, and therefore that concentration there is increasing, which again is that increase in particles increasing the collision rate, which again then is driving the reaction in the reverse direction. These graphs tell us a lot of information, and we'll be using them a bit over the course, and we'll discuss these a little bit further in class. See you then.